Today we're going to learn about spherical coordinates. So this is one more transformation of a triple integral from rectangular into a different realm. We're going to call it spherical coordinates. And we use spherical coordinates in order to evaluate triple integrals that are being integrated over regions that are bounded by cones and or spheres. They end up being very convenient to use and can sometimes make an integral that's impossible to evaluate, not just possible, but almost simple. Okay. Now, the difficult part is just like, what are spherical coordinates? How do we use them? What are all the conversions and all of that stuff? Okay. So first of all, we have two angles. We also have two angles and we have a radius. The two angles are, and I'm going to go to this first picture here to highlight them. We have theta, and notice that theta creates an angle with the positive x-axis. The next angle that we have is this weird looking one. It's called phi. Some people call it phi, but the more accepted pronunciation is phi. And phi makes an angle with the positive z-axis. Okay, so they both make angles with one of the axes. One is the positive x, one is the positive z. Rho is it's a radius, but it's given a different name. So we use rho when we're using spherical coordinates in order to kind of delineate it from the radius r that we know is created by being just the radial arm for theta. Okay, so in polar coordinates and cylindrical coordinates, r measured the radial arm that comes off of the positive x-axis. Rho is also a radial arm, but it creates a positive angle with the x-axis and an angle with the positive z-axis. So that's kind of the difference. Let's see, so our notation, the order that we give our coordinate or our ordered triplet in is rho, theta, phi. Let's see, theta typically takes on values between 0 and 2 pi, although it is not totally impossible for theta to take on values that are, like minus pi halves to pi halves. But in spherical coordinates, they tend to just be positive angles between 0 and 2 pi. Phi, on the other hand, only sweeps down by pi units. So what that means, just in a quick little picture here, if I have a little 3D octant and positive z points up, if I have some radial arm, say here, and I sweep it pi units, it looks like it's going to end up at the negative z-axis, and it cannot go further, okay? So I like to think of phi as the angle that can sweep out an orange slice, if you will. Theta will then take that slice and it'll spin it around the positive z-axis for us to get a three-dimensional shape, okay? The phi cannot go past pi. It is always somewhere between 0 and pi. And then rho, because rho is a radial arm, rho is always positive, okay? All right, so we have these interesting little pictures right here. And basically what we've got right here is the different triangles that are created when we connect rho to the z-axis, or if we connect r, or I should say a projection of rho onto the x-axis, when that gets connected to, let me say that again, when we get a projection of rho onto the xy plane, and then we connect that to the x-axis in a right angle, we get these two different triangles. And then we're able to get some different relationships using sines and cosines, and the fact that we know the length of rho, and we've got theta and we've got phi. So like we remember before, so this third picture, this is showing that theta is the angle on the xy plane revolving around the z-axis. Okay, I want to talk a little bit about, let's see, this length right here, like where that comes from. So we can see there's a right triangle here. It doesn't look very right, but I'm going to draw it as a right triangle a little bit more clearly. Okay, so there's the right angle. And then let's see, the hypotenuse is rho. And it looks like from how I've drawn this, this is my z, right? Is that my z? No, this is my z. Goodness, this is hard. Okay, so no, I'm sorry. This is z, and then adjacent to z is going to be phi. Okay, so if I was to take cosine of phi is going to be my adjacent side z over my hypotenuse rho. And so if I solve for z, then z is going to equal rho cosine of phi. Okay, so that's how we're getting this length right here. And then we could similarly figure out a value using sine of phi that gives us this length right here on this particular triangle. Okay. All right, and this actually also gives us some of our conversions that we need, but I also have them listed right here. So it's not something that you have to like go to a triangle every time to try to remember. I also give these in our formula sheet. So I have them right here, but make sure to check out your formula sheet to see what the conversion table looks like. I have everything for rectangular to cylindrical to spherical, okay? Now, if we want to go from spherical to rectangular, we have these three conversions. We have that x is equal to rho sine phi cosine theta. We have that y is equal to rho sine phi sine theta. And then we have that z is equal to rho cosine of phi. Okay? You do need to know these and how to use them, really. If you were given spherical coordinates, could you come up with rectangular coordinates using these? Rectangular to spherical, we have that rho squared is equal to x squared plus y squared plus z squared. That should kind of make sense given what we have from cylindrical. So just to, recall, x squared plus y squared was equal to r squared in cylindrical. So this is kind of the analogy going to spherical. Right? Now our radial arm is called rho. Now we have a third variable. And so rho squared is equal to x squared plus y squared plus z squared. Tangent of theta is still y over x. Cosine of phi, that kind of comes directly from up above. If you solve for cosine of phi in the equation above, you get cosine of phi is z over rho. Okay. On the flip side, we could get that phi is equal to cosine inverse of z over rho. Similarly to how on the tangent of theta, if we take arctan of both sides, we get theta is equal to arctan of y over x. Okay. Now, if we want to go between spherical and cylindrical, we also have conversions. We have that r, the radius that exists on the xy plane, is equal to rho sine phi. We have that theta is equal to theta. That doesn't change. And then we could find z by calculating rho cosine phi. And if we want to go the other way around, cylindrical to spherical, well, if you recall, r squared is x squared plus y squared. So we could replace x squared plus y squared with r squared, right? And then we'd be able to calculate rho squared by just putting in r squared and z squared and adding them. Theta would still be theta. And then cosine of phi would give me z over rho. And so I could then easily solve for z in there. Or sorry, cylindrical to spherical. Then I could easily solve for phi. there. Okay, so those are all our conversions. We're going to practice a little bit using those. But first I want to talk about a few very common equations that show up for us and what they are. It's important that we know what we're working with even if we have an equation in spherical coordinates. So if I tell you rho equals c, what you have to remember is that rho represents the radial arm for a sphere. So if I tell you that rho is equal to a number c, I am telling you the radius of a sphere. And you can assume that I just gave you the equation of a sphere. Okay, so let's just see how that works out though. What if I square both sides? Well, then rho squared is equal to c squared. And then if I switch rho squared over to rectangular coordinates, I get x squared plus y squared plus z squared is equal to c squared. And now we can see the equation of a sphere. So there really is a direct conversion from the spherical equation to the rectangular equation that shows us, oh yeah, that's a sphere. Now if theta is equal to c, we already saw one of these when we were working with cylindrical coordinates. This is a half plane because this is independent of phi. So we would just say that phi goes between 0 and pi. It is also independent of rho. So we could just say that rho is simply greater than or equal to 0, goes on forever. And then theta being equal to c, well, if we create some angle c, which is done right here, with a positive x-axis, then we would draw a line coming out of that positive x-axis. That would be our rho. And we could draw that out infinitely. We usually stop because we can't actually draw infinity, but then we could draw the plane that represents that. And so theta equals a number is always giving you a half plane that cuts through the angle C on the xy plane. If we were given phi equals c, that's a little bit different, okay? So what's happening here with phi equals c is that it's independent of theta, which means that theta is going to take on all of its values, 0 to 2 pi. It is also independent of rho, which means rho is simply greater than or equal to 0. It goes on forever. So what I'm going to do here real quick is I've got the pictures of cones right here, but let's just see this. So I've got an x, y, z octant, and if I was to draw out the radial arm rho, I'll just place it right here. We'll call this angle C, and here's my radial arm rho. Now theta is going to take this radial arm and it's going to sweep it around, and then it'll come all the way back. And that's going to create a cone. Okay, so anytime you see an equation, phi equals some number or some angle, that's giving you the equation of a cone. A half cone, really, because a cone is both upward facing and downward facing. Now, if c is between 0 and pi halves, then it is a cone above the xy plane. And if c is between pi halves and pi, then the cone is below the xy plane. All right, now in order to integrate with spherical coordinates, we have to be able to convert the rectangular differential, the dx, dy, dz, over to a spherical differential. And so your book does go over a geometric way of coming up with that differential. I'm going to go over a calculation way that would be covered in a later section that we don't cover in this book. But it is nevertheless a super useful method because you don't have to rely on geometry and actually having to be able to see what you're doing. So we're going to calculate a Jacobian of our conversion. And what we actually need, though, is the magnitude of the Jacobian. So that just means we need the positive value. So we're going to get the positive of whatever we get after we calculate the determinant. Because remember, the Jacobian is simply calculating a determinant. Now, we have these coordinates. Rho, or x is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. So for each of those coordinates, x, y, and z, we need to calculate a first partial with respect to rho, theta, and phi. So I have my determinant set up so that we can see in the first row, we have the first partials for x. Second row are the first partials for y. Third row are the first partials for z. I've gone ahead and calculated all these first partials. You can kind of double check that work on your own if this is something that interests you in being able to calculate on your own. Make sure that when you take a first partial that you also put in the differential to indicate what first partial you just took. So if you just found x sub rho, then you need to have a d rho in there. If it's x sub theta, you need a d theta. X sub phi, you need a d phi. This is a 3x3 determinant, which is really kind of painful. I actually expanded about the bottom row, and across the bottom row, the signs are plus, minus, and plus. And so I would take the cosine of phi d rho, and then I would multiply that by the determinant of the 2x2 matrix that is left over after you cross out the row and column that cosine phi d rho is in. So we can see that here in this first entry. Then my second entry would be minus 0 times a 2x2 determinant, which I don't even need to worry about what that determinant is because 0 times anything is 0. So I don't even show that here. Plus, my third one is the negative rho sine phi d phi, and that gets multiplied by the 2x2 determinant of the 4 entries that remain after you cross out the row and column that minus rho sine phi d phi is in, and that's showing up right here. After that, we have a few 2x2 determinants. Remember, it's plus and then it's minus. So it looks like kind of a cross product sort of thing that's happening here. And there's a lot of algebra for you to get lost in, for sure. I have tried to show all my steps to try to make it clear what's going on. I'm not going to just read it out loud to you though, but definitely, maybe take the time to read through it and see if it's making sense what I've done. In the end, what we end up getting is this expression right here. Minus rho squared sine phi d rho d theta d phi times cosine squared phi plus sine squared phi. Well, that cosine squared phi plus sine squared phi is equal to 1. And then we have to remember that we take the positive of the Jacobian, and so that gives us finally our differential. dv, or dx dy dz, is going to be replaced by rho squared sine phi d rho d theta d phi. You can change the order of those differentials, but the rho squared sine phi must be there. You need to know this. I will give you all the other conversions that you need, but you need to know your differentials. Just like we needed to know them for cylindrical and polar, we need to know them for spherical, okay? So make sure you take the time and put in the effort to remember your differential. You can always write it down on your test as soon as you get your test, and then you can, focus on remembering other things for your exam. All right. Once we have all that, we know what the differential is supposed to be. We know what what x is supposed to equal, y and z are supposed to equal. What we do then is we're going to convert a rectangular integral. And so here we have f of x, y, z dv. We need to convert the integrand by changing all x's, y's, and z's into their corresponding parts that we have listed in here. And then we need to replace dv with that rho squared sine phi d rho d theta d phi. Okay? Right here I have generic bounds on this. I'm not really concerned with what those actually even say. The point is that they are bounds. That's it. Okay? We would have to figure those out in any given problem that we're working with. All right, we're going to start with converting rectangular coordinates to spherical coordinates, see how that is done. In particular, we're starting with rectangular coordinates -2, 2 root 3, and 4. And we want to change those to spherical coordinates. Now, these are these are x, y, and z. And we want to see what they are going to look like in spherical coordinates. So we have a couple of equations that are going to help us. Since we know, let's see, let me write this out. We want rho, theta, phi. Got to keep my eye on the ball, what it is I'm looking for. I do know that rho squared is equal to x squared plus y squared plus z squared. That means that rho is equal to the square root of that sum of squares. So I can take my x, y, and z, square them, and put them under this square root. You get -2 squared plus 2 root 3 all squared plus 4 squared. This all adds up to, let's see, 32, which simplifies to be 4 square roots of 2. This is my rho value. Okay, not too bad. I need theta next. And I have to remember that theta is equal to the arctan of y over x. So I'm going to plug in my y and my x and take the arctan of them. We're looking at the arctan of 2 square root 3 over -2, which simplifies to be the arctan of -√3. Now what I have to remember is what quadrant the particular x and y value that I have would put me in. So I have a negative x value and a positive y value. That would be in quadrant 2. Okay, so I need to make sure that when I calculate arctan of -√3, that the angle that I get actually is in quadrant 2. And if it's not, I need to add pi units in order to get there. Well, it turns out that the arctan of -√3 is equal to 2 pi over 3, which is in quadrant 2. So I'm good with that. The last thing we want to find is we need phi, okay? And we have that, well, we know cosine of phi is equal to z over rho, which means phi is equal to cosine inverse of z over rho. And now you're going to see that we can't actually find phi until we have rho. Okay, we have z already. We can put that in. And we do have rho, but we didn't in the beginning. Rho is 4 times root 2, so I'll plug that in. This simplifies to cosine inverse of 1 over the square root of 2. And that's just going to be pi over 4. Okay, now let's see. We just need to go ahead and write out our spherical coordinates. Rho, theta, phi is equal to 4 square root 2, 2 pi over 3, and pi over 4. That's our final answer. All right, in the next example, we're going the other way. We're going to convert spherical coordinates to rectangular coordinates and see what we get. We are starting off with a rho, theta, and phi value. I always like to label them just so I know what I'm working with. All right, so rho is 3, theta is 7 pi over 4, and phi is 5 pi over 6. We do have some equations that give us our values almost directly. So our conversion factors are that x is equal to rho sine of phi cosine of theta. So all I need to do is plug in rho, phi, and theta. Rho is 3. Phi is 5 pi over 6. And theta is 7 pi over 4. Okay. Sine of 5 pi over 6 is going to give us 1/2. Cosine of 7 pi over 4 is going to give us root 2 over 2. So this simplifies to give us 3 square root 2 over 4. That's our x value. Y is equal to rho sine phi times sine of theta. So again, I plug in my rho, phi, and theta values. Rho is 3, phi is 5 pi over 6, and theta, we're now taking sine of 7 pi over 4. Okay, this gives me again 3 times 1/2, but now sine of 7 pi over 4 is a negative root 2 over 2. So now we get negative 3 square root 2 over 4. All right, last one. Z is equal to rho cosine of phi. So I plug in rho and phi. I get 3 cosine of 5 pi over 6. The cosine of 5 pi over 6 is going to be a negative square root 3 over 2. So this is negative 3 square root 3 over 2. And now we have all of our values. So x, y, z is equal to 3 square root 2 over 4, negative 3 square root 2 over 4, and negative 3 square root 3 over 2. This rectangular coordinate will be in the same place as that spherical coordinate. Okay, so that's how you go back and forth between the two. Let's go ahead and see if we can describe a few regions based on some of the things we've already talked about, and just, maybe even doing some conversions to help us out. So I've got rho equals A, and I forgot what it is. Let's just say that that's what happened. Rho equals A. I have to start thinking about what sorts of equations I have. I don't really have anything for just plain old rho in terms of x, y, and z, but I do have something for rho squared. So I'm going to square both sides. Rho squared is a squared. We have already seen this before. And then rho squared would be replaced with x squared plus y squared plus z squared is equal to a squared. Well, that's just going to be a sphere with radius a. And that's exactly what it is. Okay, so if you see rho equals a, you want to start getting used to that, oh, that's just a sphere that's being described with spherical coordinates. That's it. Theta equals a, we already saw that that is a half plane. And it's a half plane because what ends up happening is we have that there is this angle created with the positive x-axis. We'll call that angle A. And then we have you could think of our rho. Our rho is infinite, and that's our radial arm. And it's gonna, kind of sweep down and go right through our plane. And so we're gonna end up, or our line, I should say, we're gonna end up getting this infinite plane, because remember the rho arm or the radial arm is infinitely long, and it's just sweeping things out. And they actually do dip down into the negative z. Okay, it's a terrible drawing, I'm sorry. But hopefully you can see what we have here is a half plane. Because phi does not sweep beyond the negative z-axis, this will stop at the negative z-axis. So it really is just a half plane. And we could give it a little bit more description. It's a half plane with an angle A with the positive x-axis. All right, phi equals A. So remember, phi is the angle created with the positive z-axis. So we could think of it as, let's say, here we go. And this is A. Rho is infinite. We have no restrictions on rho. This equation is independent of rho and independent of theta. So what that means is that this radial arm actually goes on forever, and theta takes this infinite radial arm and sweeps it around by a full 2 pi units. And we end up with the upper half cone. If A is between 0 and pi halves, and it is the lower half cone if A is between pi halves and pi. Okay? Make sure that you get comfortable, especially with rho equals A being a sphere and phi equals A being a cone. It'll make things a lot easier for you. Okay. Now we want to describe some objects using spherical coordinates. And what I mean by that is coming up with the intervals of rho, theta, and phi that would give us the shape that we're being given. Okay? So if we're told we have a sphere of radius 3 centered at 0, 0, 0. What that tells me, first of all, the radius of 3 is that rho is going between 0 and 3. Okay? What that also tells me is that phi and theta are maxing out on the values that they have. So phi is going to start at the positive z-axis. It's going to sweep all the way down to the negative z-axis with an angle of pi. Then theta is going to take that arc that was just traced out by rho and phi, and it's going to swing it around by 2 pi radians to create a full sphere. Okay, so these intervals all together describe a sphere of radius 3. The reason this is important is that we are going to be integrating over these three-dimensional objects. Like you could be integrating over a sphere of radius 3. That means you need to be able to come up with all of the bounds for rho, theta, and phi on your integral. So that's why we're doing this, little exercise here. In part B, we're asked to describe the portion of the sphere, x squared plus y squared plus z squared equals 2, lying in the octant where x and y are both positive or equal to 0, and z is negative. So if all three, with x and y being both positive, I'm thinking it's either octant 1 or octant 5. Okay, so if I draw this, with the fact that z is negative means that we've got a sphere that is down in the negative octant, so that's going to be octant 5. And so we could kind of see it's that portion of the sphere right there. And that's it. So we're in the 5th octant. All right. In order to be in the 5th octant, let's first deal with rho. I can see since the equation of the sphere is equal to 2, this tells me that rho goes between 0 and square root 2. Because we are below the xy plane, that tells me that phi starts at pi halves and then continues on to pi. So that gets us, the entirety of the 5th octant there. But then theta is starting at 0 because it's starting with the x-axis and it stops at the y-axis. And so that means theta only sweeps out by pi halves. Okay? These intervals describe that quarter. Is that a quarter? No, that's an eighth. That eighth of the sphere that's down in the 5th octant. All right. The plane x equals y. All right. Well, remember that up here we had if theta equals a number, that gives us a half plane. So let's think about that. If we want, this is a full plane, x equals y. That full plane would bisect the 1st octant and the 3rd octant. So something like this. And so we don't just want the part that is going through the 1st octant, we also want the part that's going through the 3rd octant. In the 1st octant, the angle is pi fourths. That's the one that bisects the x and y axes in the 1st quadrant. And if we want the other one, we would have to swing all the way around to get over to here, in the third octant, and that is going to be, so pi fourths, 2 pi fourths, 3 pi fourths, 5 pi fourths. So it's like we actually need two ways to describe this. And the first one is that theta is equal to pi fourths and theta is equal to 5 pi fourths. It's the only way we can get the full plane. I want to show you another way to deal with this though. Let's look at this. If I divide both sides by x, I get 1 on one side and I get y over x on the other side. Now, if I take arctangent of both sides, I get arctan of 1 is equal to arctan of y over x. Okay, well, arctan of 1 is pi fourths. And so that's telling me that arctan of y over x is equal to pi fourths, okay? Or 5 pi over 4, because arctan of 1 is pi over 4, but it's also plus pi to get you to the 5 pi over 4, okay? So that's another way to kind of describe it, or to get to how we're describing it. You choose the way that makes the most sense for you, though. All right, part D, the half cone z equals the square root of x squared plus y squared. All right, I'm going to start from my rectangular coordinates and see if I can work my way over to spherical coordinates, okay, so that I can get myself a way to describe this. If I was to square both sides, I have z squared is equal to x squared plus y squared. Now I want you to recall that rho squared is equal to x squared plus y squared plus z squared. Okay? That means that x squared plus y squared is equal to rho squared minus z squared. So now I'm going to replace my x squared plus y squared with rho squared minus z squared. So that means now I have z squared equals rho squared without z squared. It means rho squared minus z squared. If I was to move my, well, actually what I could do is I could replace z. So here's another recall. Z is equal to rho cosine of phi, and that will get me fully into spherical coordinates. So I'm going to replace all my z's with rho cosine phi and square them. Rho squared cosine squared of phi equals rho squared minus rho squared cosine squared of phi. I'm going to move everything to one side of the equal sign. We get 2 rho squared cosine squared of phi minus rho squared is equal to 0. Factor out a rho squared. Leave behind a 2 cosine squared of phi minus 1 is equal to 0. This tells me rho equals 0, which that doesn't help me at all. Or cosine squared of phi is equal to 1/2, which means cosine of phi is equal to plus or minus 1 over the square root of 2. That means that phi is equal to cosine inverse of 1 over square root 2, or cosine inverse of negative 1 over square root 2. Now I'm going to come up here and finish off. That means that phi is equal to pi over 4 or 3 pi over 4 after we take the cosine inverses. Now this half cone, z equals the square root of x squared plus y squared, that's a positive or upward facing cone. And so that means we have to choose pi fourths, and we choose phi equals pi fourths because z is positive, since z is equal to a positive square root. Okay? So the way we would describe the half cone is just simply with phi equals pi over 4, and that's it. If it was the half cone z equals negative square root of x squared plus y squared, then I would have chosen phi equals 3 pi over 4. Just so you're clear on like when you would choose one over the other. All right. Finally, we're going to evaluate some integrals. I'm actually going to stop this video now though, and we'll do this in 2 parts. So we're done with identifying and changing things and, getting comfortable with, or maybe not comfortable, but familiar with some of the conversions. In the next part, we'll work through a bunch of integrals and see how to work with spherical coordinates in integration. If you do have any questions, please reach out.